Hello! Hello, 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 hello. How is everybody? We didn't get a morning nerds from Isaac. There it is. Isaac's at 2.2k valence electrons. Friday. We are at the end of quarantine week 3. I have one emote. The other emotes I have to get approved, but so I have 3 emotes that are ready to go. So you can use your valence electrons to unlock them for 24 hours if you want. Or you can save up your valence electrons until you get 10,000 and try to redeem them to make me dab. Exactly. Hey, Max uses valence electrons. Thanks, Phalangion. Number 1. I'm tired. I was gonna check. I don't know if they did. They had a meeting last night about it, but I'm not sure if they've published on the student side yet. Nope, not published yet. So yeah, they got an email that was saying that they were gonna have a thing about it last night, but I wasn't able to attend. So yeah, they haven't said. So they invited me to like a conference thing last night, but I had to teach my BYU class, so I don't know what they have mentioned yet. So yeah, they should have a community thing out today. They said information covered during the presentation will be released broadly to the AP community on Friday, April 3rd. But it looks like the page isn't updated yet. So this website is supposed to be updated when they have more information, but they haven't. They don't have anything else on there yet. So I assume that website will get updated later today. Yeah, so I figured out there. I just tweaked a few things. I think it's actually my heating screwed it up a little bit too. So we'll see. Yeah, hopefully, Isaac, it'll be up by this afternoon. I don't know if they had like a time goal. We're not necessarily going to be taking notes, but we're going to be working through the problems. So if you want to, just jot down some answers to the questions, because we're going to go through the 2015 exam. And so we can, work through some of the problems, answer some of the questions you might have to do that. And so I'll be using this to do that. So we're not gonna do like Unit 3 review until a week from Monday. Nothing next week because of spring break. You guys just work on your review books, kind of on your own. And then if you have any questions, I'll be available, but not as dedicatedly available. It'll be more hit or miss on getting me to reply to things because it's my spring break too. So. No, actually, they're almost done. They only have a week and a half less of the semester. So I'll still be teaching by BYU class on Tuesday and Thursday nights. We're doing organic chemistry. Well, they're just semesters ending in a week and a half. 2 weeks. They have finals in 2 weeks. So yeah, if you want to learn some OChem nomenclature, feel free to tune in for that next week for BYU. And then high school we have our esports team. We've got a scrim against who are we playing? Against Pleasant Grove on Monday night, and then we're playing Salem Hills on Tuesday. So I'll be streaming those as well. Excuse me. DJ apparently has a vendetta against Salem Hills. Sorry, I'm just fixing this. Vendetta is the perfect word. Good, I'm glad. Okay. It's 10:05, right? So we got most people in. What questions do we have about the 2015 exam, right? We have two ways to approach this. We can go through every question, which we won't get. We probably won't get done in an hour, or we could just look at the ones that you guys had struggles on, which is the way I would prefer to do it. But in order to that, you guys actually have to ask questions about it. Number 7. Okay, let's just dive into number 7. All right, well, let's start with 7, and then we'll ask for some other requests after that. So here we go. Question 7. Oh, this problem. This one's a good one. All right, so question 7, very last question on the test, says aluminum metal can be... Oh, this is the grading key. Let's look at the actual problem. Sorry. Oops, there we go. So number 7 says aluminum metal can be recycled from scrap metal by melting the metal to evaporate impurities. Calculate the amount of heat needed to purify. Yeah, rates are a big thing, Lauren. We're going to hit rates in our review in another week or two. So letter A says calculate the amount of heat needed to purify 1 mole of aluminum, originally at 298 Kelvin, by melting it. The melting point is 933. The molar heat capacity is 24 joules per mole. The heat of fusion is this. Okay. So when we look at this first problem, I'm gonna jot down some info. Then I'll go back to the document camera. So we know we have 1 mole of aluminum. And then it's at 298 Kelvin. Melting point is 933 Kelvin. The molar heat capacity is 24 joules per mole Kelvin. And the delta H of fusion is 10.7. Okay, cool. Let's go to the problem. All right, so this is the important information for the problem. 1 mole of aluminum at 298 Kelvin. It melts at 933. And so we want to know how much energy is needed to melt it, right? So we have the delta H fusion, then we have the specific heat. So what we've got is we've got 2 heat processes. If you remember, I don't know if you guys remember the curve that kind of looked like this, where we had heating the solid, melting the solid, heating the liquid, melting the, or boiling the liquid, heating the gas. And so what we're doing here is we're focusing in on this part of the process. We're going to heat up the liquid, and then we're going to melt it. And so we have we have 2 Q's that we're calculating. We need to calculate the Q associated with heating, and we needed to calculate the Q associated with melting. Right? So the Q for heating, whenever we're changing temperature, you got to remember Q when we're changing temperature is MC delta T, usually. But in this case, because they gave us the C in terms of moles, we can actually, instead of mass, we can use moles here. Because usually specific heat is in joules per gram Kelvin or gram degree C. But in this case, they've given it in terms of moles, joules per mole. So we can take the moles times the joules per mole Kelvin times the delta T and get the heat. So this one's relatively straightforward. We know we have 1 mole, so we say 1 mole times 24 joules per mole Kelvin. And then our change in temperature. Our change in temperature is our final temperature, the melting point. That's how hot we have to get it, minus the initial temperature, 298. So this is going to be 933 minus 298 Kelvin. So I'm going to, we'll put this down. So the Q of heating equals whatever that math is. Let's see, 933 minus 298 times 24. So it's a pretty good number. It's 15,000 joules. The problem with that, Isaac, is if you did that, you would have to change C to be, instead of joules per mole Kelvin, you'd have to convert it to be joules per gram Kelvin. And so you'd have to multiply by the molar mass and then divide by molar mass. And so it cancels out anyway. And so just leaving it in moles is the most straightforward way to do the problem. So it's 15 kilojoules. Okay. Now the melting, right? The melting, we can use the delta H of fusion and just do a factor label. So how many kilojoules equals, the 1 mole of melting? We know that 1 mole requires 10.7 kilojoules. So remember, we can use the delta H as a conversion factor, right? We can use the delta H, this 10.7 kilojoules per mole, and because we're using 1 mole in our problem, it's just 10.7. And so the total heat change is the sum of our 15 kilojoules plus the 10.7 kilojoules, which is 26 kilojoules. Yeah, they're posted to YouTube, Mikey. And then I put links on Canvas. All right, so we get 26 kilojoules. I think, yeah, and so if we look at the grading key, right, it says, it shows the Q equals MC delta T calculation, right? And then it shows that, it takes 10.7 joules per mole, and so you add together, you get 26. Yeah, no problem, Mikey. So apparently we get 1 point for calculating the amount of heat needed to raise the temperature. So we get 1 point for the MC calculation, and then we get 1 point for adding the two together. And then letter B, so letter B says the equation for the overall process is shown below, which requires less energy, recycling existing aluminum or extracting aluminum from aluminum oxide. So let's go back to the problem, right? So what we have is we have this equation where it says if we take aluminum oxide to produce solid aluminum, the delta H here is 1,675 kilojoules per mole. But that's to make 2 moles of aluminum. So if we're making 1 mole of aluminum, it would require half as much, or it'd be 800, right? Because for the equation, there's a 2 here, so if we did half of it, it would be 800. How does 800 kilojoules compare to 26 kilojoules? It's obviously a lot a lot higher. And so in the answer here, they basically say, oh yeah, so you take 1675, 2 to 1, right, 837. So they want you to get the equal number of moles for comparison. Now, technically, instead of dividing this by 2, you also could have taken your answer from A and multiplied it by 2. That would have given you credit as well to say, 1675 versus 52 or 837 versus 26. And you can say, oh yeah, so 26 is much less than 837. Recycling requires a whole lot less energy. And that's 4 points, right? Which is not too bad. You just had to remember your calculations. Okay, Haley, you said number 5. You wanted to go through number 5? Oop, 5 is a rates. Yay, rates. Okay. Whoops. DJ, how many total points equals what score? They have it at the very end of the grading key. Oh, no, they don't. Oh, they usually do. Ah, shoot. I should have. I have that somewhere. I'll look at that and let you know. Yeah, it's on my other laptop. I'll get that updated and up today so you guys can have that. Yeah, it's out of 36. It's usually somewhere around like an 80% is a 5. So somewhere around like a 29 is a 5. But I'll double check. I've got it somewhere on my laptop. So Lauren, remember, for a 3, all you need is like a 45% to 50%. So you just need like 17-ish, and that's a 3. Yeah, that should be around a 4, Isaac. So yeah, the approximate breakdown is like 80% is a 5, 60% is a 4, 40% is a 3, like 20% is a 2 ish. But yeah. Yeah. So remember, you can miss a lot more. So Lauren, remember, this is our first practice, right? Hopefully the point is that as we keep doing more of these each week, that your score keeps going up and you keep doing better. Hi Slayer Darth. Okay, so number 5. Number 5 says a whole lot of things. We've got a whole lot of words, right? So we apparently have oh, hi Slayer. Welcome to the stream. We're going through one of the past AP chemistry exams. Well, hopefully you can learn something. So in this problem, we're using apparently blue food coloring. This sodium whatever that is apparently blue. And we can oxidize it by using bleach, which is hypochlorite ions, to form colorless products as represented by the equation above. Student uses a spectrophotometer, fancy, set at a wavelength of 635 to study the absorbance of the food coloring over time. In the study, bleach is present in large amounts, blah, 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 blah. Oh, so bleach is present in large excess. So the hypochlorite ion is constant. That's an important idea. Student uses data to generate the graphs. Okay, so we've got 3 graphs. We have absorbance versus time. We have natural log of the absorbance versus time. Cool. And we have 1 over the absorbance versus time. Okay. And so if you remember rates, you have to remember rates in order to answer this question. Okay. If we remember rates, with rates we had 0th order, 1st order, and 2nd order. Right, with their respective rate laws. Now, even if you don't have this memorized, if you take a quick look at the formula sheet, oh, they don't actually say it on the formula sheet. Lame, never mind. So you have to remember 0th order is concentration versus time. 1st order is the natural log of the concentration versus time. And 2nd order is 1 over the concentration versus time. And this is what gives you a linear graph. And so if we look back at the graph, right, we can see that the natural log of the concentration versus time is linear, right? This one's curved and that one's curved. And so that way we know that our reaction here is 1st order. Okay, because this graph is linear, that tells us the reaction is 1st order. Okay, if it had been this first one, then it would, if this one had been linear, it would have been 0 order, and if this one had been, sorry, I'm not pointing. If 1 over the absorbance had been 1st order, words. Okay, if the 1 over the absorbance had been linear, it would have been 2nd order. And if the absorbance versus time had been linear, it would have been 0 order. But because the natural log of the absorbance versus time is linear, it's 1st order. Superscript dash. Yeah. That's a negative symbol, Slayer. Negative symbol. Okay, so letter A, based on the graphs above, what's the order? It's first order. Done. Easy point. That should have been an easy point. Okay, letter B. The order tells you the equations to use, right? So let's go to this next one. So it says, well, it also tells you like, so that's a good conceptual question, Bryce. So remember, a first order reaction, as you double the concentration, the rate doubles. With a zeroth order, if you double the concentration, and the rate doesn't change. And with a second order, if you double the concentration, the rate quadruples, right? It's back to our rate laws, where rate equals K times A to the M. Right, so this is our initial concentration raised to the M power, and that power is the order, whether it's zero order, first order, or second order. And then this also leads us to our integrated rate laws. No, we're not going to go through the calculus, but you just need to know the equations. You need to know that for a zeroth order, the concentration of A at time t is equal to negative KT plus the concentration of A initially, right? And then for first order, the natural log of the concentration of A is equal to negative KT plus the natural log of the concentration of A at time t. And 1 over the concentration of A is equal to positive KT plus 1 over the concentration of A. That's not T, that's a not initially. Right, so these equations are on the blue sheet. Yep, they're on the blue sheet. But you need to, they don't tell you what they are, so you need to know that this equation is zero order, this equation is first order, and this equation is second order, because that is not on the blue sheet. Here, I'll pull it up and show you. So here's our equation sheet, and then there they are. So if we look kinetics, right, so it has it has the first order and it has the second order. It doesn't even list the zeroth order. It assumes that you can understand the zeroth order based on this. So they're in a slightly different, they've subtracted the initials onto the other side, but it's the same thing. Okay, so back to problem number 5. All right, so part B says, the reaction is known to be first order with respect to bleach. So now we're looking at the bleach instead of the food coloring. So food coloring was for part A, all those graphs were per food coloring, but now we're talking about bleach. So in the second experiment, the student prepares solutions of food coloring and bleach with concentrations that differ from those used in the first experiment. So a different experiment. When the solutions are combined, the student observes that the reaction mixture reaches an absorbance near zero too rapidly. So he's saying that the reaction is happening too fast. In order to correct the problem, the student proposes the following 3 possible modifications. So we're trying to slow down the experiment, right? So which of these are going to result in a slowing of the experiment? Increasing the temperature, increasing the concentration of food coloring, increasing the concentration of the bleach. Circle the one proposed modification that could correct the problem. Explain how that modification increases the time for the reaction mixture to reach an absorbance near zero. Okay, so this is actually interesting because we're not slowing down the reaction like you may have thought and I may have said at the start of the prompt, but we're trying to make the color last longer. So which of these changes is going to make the color last longer? If we just increase the temperature, right? So just increasing the temperature, that's going to make the reaction go faster because higher temperatures, we think about kinetic molecular theory, they're going to bump into each other faster and that's going to cause the reaction to go faster and so that'll clear away faster. If we add more blue, right, it'll take longer for all of that blue stuff to react. And so that's why increasing the food coloring, that's why this is the correct answer, because we're adding more blue stuff. So you kind of have to know that the blue stuff, actually, you know that in the prompt if you look up. Oops. So they tell you that the dye is blue and it reacts with bleach to make some colorless products. And so if we want it to be blue for longer, if we up the amount of blue we have, that'll make it blue longer. If we increase the concentration of the bleach, that'll just make the food coloring go away faster. So the only one that works is the food coloring. Explain how that modification increases the time. Basically say if we start with more blue, it takes more time for the amount of bleach to reach it. What does the answer key say? They probably say it a little more technically. Oh, there it is. They say increasing the concentration of food coloring should be circled. That's 1 point. So you get 1 point for just circling it. That's nice. And then the second point comes from if the initial concentration of the blue food coloring is increased, then more time is required for the coloring to change. Yeah, so basically more blue, it takes longer for the blue to react. Good, Sonaris. I'm glad you got a point. All right, and then part C says, in another experiment, a student wishes to study the oxidation of red food coloring with bleach. How would the student need to modify the original experimental procedure to determine the order? Okay, so this is a little tricky. You have to know, okay, what's the difference between red and blue? Obviously, colors, right? But the wavelength, yeah. If we go into the original prompt of the problem, it says a student uses a spectrophotometer set at 635. And so that specific wavelength is for blue. Hello, Flepsy. And so if we're going to change it to red, we have to change the color that we're looking at. We have to change the wavelength. And so that's what we would need to do in order to make the modification. So in part C, all you should have to say is you got to change it to a different wavelength. Which I don't love this problem because it kind of gets lost in the prompt if you don't read the prompt very carefully. Right? So you have to understand this idea of what they're doing. So the spectrometer, that's a good question, Lauren. So the way a spectrophotometer works, right? So we can imagine that we have some sort of a light source, right? And so this light bulb is going to be shining light through our sample. Okay, and as that light passes through, on the other side here we have some sort of a detector. Now, that detector is not like, it's not like our eyes where we can, recognize several colors. A lot of detectors have to be set to a specific wavelength to look for a specific color. And so if this is blue, you want to tune it to be set to look at blue being absorbed. If it's red, you would have to set the detector, so you have to fine tune it to detect what's going to get out. So you'll get this graph. Excuse me. You'll get this graph that shows you, varying, intensities based on whatever your experiment might be. Okay, and so if you change the wavelength, you'll set it for different colors. So basically, as Isaac's saying, it's a magical black box that you can tune to see how dark something is in terms of its color. And the darker something is, the greater the absorbance. So it's a cool black box. Okay. If I set it to the wrong wavelength, it depends. It depends on the actual spectrum you're looking at. You might still get some sort of a graph. So this is looking at like a wave or a band of wavelengths. You would set the detector at like a specific wavelength. And so it would move up or down. Just kind of depends on the graph. Thanks for the follow, Slayer. All right. Yeah, I'm not doing a great job describing that, but that's okay. What other problems did we have? What other questions did we have? Number 3. Ooh, that's a long problem, Bryce. Any particular part of number 3 or just the whole thing? E. Okay. So let's look. Oh, it's a titration curve. Okay. So number 3. So I should be able to do number 3 quick enough. Let's look through it. Okay. So number 3 says potassium sorbate, a molar mass of 150 grams per mole, is commonly added to soft drinks as a preservative. Oh, interesting. A stock solution of potassium sorbate of known concentration must be prepared. A student titrates 45 milliliters of the stock solution with 1.25 molar hydrochloric acid using both an indicator and a pH meter, and then they give you the value of Ka. Okay, so letter A is simple. You should notice that these problems a lot of times they'll get a little more complex, and then the last one or two is super easy again. It's just how they word or do the problems. Okay, so let me jot down the Ka, and then I'll jump over to my paper. Okay, so for the first one, part A, you're writing the net ionic equation between KC6H7O2 and HCl. Okay, so this is going to be a double replacement reaction, right? So the K and the H are going to swap. And so we get HC6H7O2 aqueous plus KCl. Okay. In a total ionic fashion, it splits K plus, C6H7O2 minus, H plus, Cl minus. Weak acids, of course, are going to stay together. Sonaris, this is a good review from this morning. A little more complex. All right, so our potassiums cancel, chlorides cancel. Net ionic is just C6H7O2 minus plus H plus. Now, you could have just written that. You didn't even have to do the total and net ionic. You just have to have that equation written. I'm pretty sure the grading key shouldn't count you off for that. Yeah, you just have to write the equation. On the grading key, they have it written as an equilibrium, but you can have it as a forward arrow because it's mostly going to be forward anyway. Okay, part B. Part B then asks, a total of 29.95 milliliters of the 1.25 molar is required to reach the equivalence point. Calculate the concentration of the stock solution. So this is just a simple equivalence point calculation. We can use our cheater equation because it's a 1-to-1 ratio. We can say the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. The molarity of our acid was 1.25 molar. The volume of the acid was 29.95 milliliters. The molarity of the base is what we're trying to find. The volume of the base in the original prompt said it was 45 milliliters. And so just solving for x, the molarity of the base, just multiply and divide. So again, hopefully this was another easy point for you. So it's 0.832. And so that is the concentration of the K, C6H7O2. Yeah, so a factor label works too, Anna. And if you actually look at the way the AP grades it, they say that they want you to calculate the moles at equivalence and then calculate the molarity. But if your moles here is implied in either your factor label or in your M1V1 equation, they give you this point anyway. So how do you do if it's not a one-to-one ratio? Okay, so if it's not a one-to-one ratio, you can't use this equation. You would have to do a factor label. Or technically, you can use this equation with some modifications, but I don't want you to have to worry about memorizing that. Just using a factor label is fine enough. You can just do, how many moles equals 1 liter of the base. 1 liter is 1,000 milliliters. 45 milliliters required to 29.95 milliliters. 1,000 milliliters is a liter. 1.25 moles, or 1 liter is 1.25 moles. 1 to 1 moles, or 1 to 2 moles is the last step. That was really fast. If you have more questions about Bryce, I can show you that. But they usually are going to do 1-to-1 ratios. All right, let's look at part C now. Part C asks, the pH of the equivalence point of the titration is measured to be 2.54. Now, let's make sure that we understand that that makes sense. Because we're doing a weak base with a strong acid, it makes sense that the pH at the equivalence is less than 7, right? Remember, strong acid, strong base is at 7. A weak acid with a strong base is greater than 7. A weak base with a strong acid is less than 7. Okay. Which of the following indicators would be the best choice? Well, we want one that has an endpoint less than 7, but not too far, right? So Thymal Blue seems like it's a little too far. So I would probably pick Methyl Red. Oh, fine. Those idiots. Yeah, so Thymal Blue is what they want you to pick. That's right. I was debating on that. I'm dumb. All right, let's talk about why it's Thymal Blue. -1 for Gillespie. Okay, so if we imagine a titration curve, right? So this is a weak base, and so the titration curve is going to look something like that. And they're saying that this pH at equivalence is 2.54. And so they say to use an indicator that changes at a pH of 2.0. You would probably actually be okay using the other one, but they say to use an indicator at 2.0 because it's closest to the equivalence. So if they ever ask you a question like this, the answer is always going to be pick the indicator that's closest, that has the pKa closest to the pH at equivalence. So Thymal Blue in this case. And then letter D, calculate the pH at half equivalence. So the pH at half equivalence, remember, what's special about the halfway to the equivalence point? We said it so many times. pH equals pKa. It's our perfect buffer. Good call, DJ. pH equals pKa. And so we wrote down, I wrote it down on the last page. We wrote down that the Ka was 1.7 times 10 to the negative fifth. And so if we just take the negative log of that, we get 4.77. And so that's our pH equals pKa idea. Why do you take the negative log? Because that's what pKa is. So in order to go from the Ka to the pKa, you take the negative log. Remember, P is our mathematical operator that means negative log of. So pH is the negative log of the H plus. The negative decadic logarithm, right? Yeah, so P, it's a mathematical operator that says take the negative log base 10 of. So pH is the negative log of the H plus concentration. Yeah, and K, right, we take the negative log to get the pKa. Same with OH, right? The POH is the negative log of the OH concentration. Cool. Was there? I think there's a part E to the problem, right? Or a part, yeah. So if we look on the next page, oh, part E. So they want you to graph. Oops. So as they say, the initial pH and equivalence point are plotted on the graph below. Accurately sketch the titration curve on the graph below. Mark the position at half equivalence. So we just found that the half equivalence was 4.77. And so if we're here, 15, we should be here. So we should have a graph that kind of goes like something like that. Right? Which, if we look at the answer key, that's what they have. Okay. And then with an X marked at that halfway to the equivalence point. So this is the general shape. If they were to keep going with this, it would, of course, level off. That's the general shape of our titration curve. Okay. Part F then asks, the pH of a soft drink is 3.37 after the addition of our weak base. Which species, HC6HO3 or, oh, this is interesting. Okay. So this is a good thing to think about. So we have to remember our buffer equation. Henderson-Hasselbalch. So remember, in the Henderson-Hasselbalch equation, the pH equals the pKa plus the log of A minus over HA. Right? Or do I have that backwards? I always have to look at the equation sheet on this one. Where are you, equilibrium? Nope, that's right. Okay, cool. All right, so we have to remember, I'm going to, redraw this a little bit better, more accurate to what they have. And they have it kind of going like that. So we said the perfect buffer was our 4.77. Okay. Now, if we go a little bit to the left, that means we have more of the KC6H7O2. And if we're to the right, that means we have more of the acid, the HC6H7O2. Okay, because at the perfect buffer, they're equal to each other. And so if we go a little to the left, we have more weak base. A little to the right, we have more weak acid. And so if we're wondering what's true at a pH of 3.77, or sorry, 3.37, that is down below. That's, say maybe right here. And so we have more of the acid, right? You could technically also calculate it. You could plug in 3.37 here, and you could plug in 4.77 here, and you could solve for this ratio, and you could find that this ratio is less than 1, meaning that we have more of the acid than we do the base. We can do that just as a quick 3.37 minus 4.77. We take 10 to the power to undo the logarithm. And we get 0.0398. So we know that the ratio of A minus to HA equals 0.0398 to 1. So we have a whole lot more HA than we do A minus if our pH is 3.37. Technically true, Bryce. You're technically right. It's still good to talk about it because we still learned how to do this kind of a problem. But they probably won't have a question like this. They've said that they're cutting for this year because some other teachers haven't gotten to this section yet because they're slow. All right, and that's letter F. Cool. So if we look at the way it was graded, right? So for part A, you got 1 point for the equation. Part B, 2 points if you calculated the molarity. Let's look at that. We'll get to that, David. So part C says 1 point for the answer, 1 point for the correct thing. 4.77, 1 point for the correct pH. Now, if you technically calculated D wrong, oh, that would be annoying because that would lead into this being wrong and all that other stuff. Okay, so this pH curve is worth 3 points. That's huge. So we get the half equivalence with consistent with D, right? Notice they said consistent with D, so whatever you put for D should be where your X is. 1 point, so it's leveled off. It has to be horizontal-ish through here. And then 1 point for the steep drop at the end. So you had to get the right shape. If you could just draw a titration curve, that's 3 points. That's like almost 10%, right? That's huge. Okay, and then let's see. Letter F said 1 point is earned for identifying the correct species and for making a comparison involving pH with or without calculation. So David says, if I said HA would be because the pK is larger than 3.34, probably. Because they said here you can do the calculation, right? So there's the calculation of the ratio. Or you could say the concentrations are equal at equivalence, the 3H is lower than, and so, yeah. So that's this second explanation. That's why it has an or here. So you can do the calculation, or you can just explain that it's less than the perfect buffer, and so we'd have more HA. Yep, so David, you'd still get that point. All right, we've got 15 minutes left. We can still do maybe one or two more. Probably just one. Maybe one more question. What else we got? If you have more questions, right, and we don't get to whatever question you want, I'll be available in the Discord this afternoon, and so you can ask more specific questions there. I'm also going to be posting the 2016 exam, but that's not due for another 2 weeks because of spring break. Okay, what other questions do we have? Which other ones do we want to go through? We went through, what, 3, 5, and 7? So we still have 2, 4, and 6. Yeah, let's look at 4. I could probably do all of 4, Anna. Oh, so this is the grading key. Oh, sorry. So AP is advanced placement. So it's a college level chemistry class. It's the high school equivalent. You can take the class in high school, and it's the equivalent of the first year of college chemistry. So it's the freshman chemistry suite. So it's the same level as like an intro to college chem course. AP stands for advanced placement. Okay. So question number 4. Yep, no problem. So it says, answer the following questions about the solubility of calcium hydroxide. So they give us a KSP, right? So that KSP should, tune your brain to think, okay, ice tables, solubilities, molar solubilities, all those things. Okay. So we've got calcium hydroxide, KSP, 1.3 times 10 to the negative 6. All right, so the first one says write a balanced chemical equation, not too bad. Calculate the molar solubility, not too bad. And then draw some water molecules. So let's go through those. Okay, so here's our KSP. We want to first draw an equation that shows it dissolving. So calcium hydroxide, solid, in equilibrium with the calcium ions and 2 hydroxide ions. Right? So there we go. Easy point, right? First point is almost always an easy point. Second problem, calculate the molar solubility. To do that, right, we use an ice table. All right, or some sort of way to approach the equilibrium. Okay, the solid doesn't matter. We say these are zeros to begin with. As this changes to approach equilibrium, we'll have plus x and we'll have plus 2x because of the coefficient. Yes. So a solid is always going to be forming an equilibrium as it dissolves, Bryce. If this was like something that was soluble, you wouldn't be doing this kind of a problem. Whenever you have a KSP, it's going to be in equilibrium. So then we have x and 2x. And so our KSP equals the concentration of calcium times the concentration of hydroxide squared. So we plug in x times 2x quantity squared. That turns out to be 4x cubed. So we set 4x cubed equal to the KSP, and we solve for x. So 1.3 times 10 to the negative 6th equals 4x cubed. X, which is our molar solubility. 1.3 times 10 to the negative 6th divided by 4. Cube rooted. We get 0.00737. Or with proper sig figs, 0.0074. There's a 0.1 molar calcium nitrate. Oh, thanks, Maggie. Did you really do the same thing? So, I got a little overzealous in solving this problem because the problem actually mentions that you're not finding the solubility in pure water. You're finding the solubility in 0.1 molar calcium nitrate. And so your calcium ions are not 0, your calcium ions are 0.1. So this is sometimes called the common ion effect. And so what that means is that instead of this being 0 here, we should have used 0.1 there. And if we do that, I'll just do it on the next piece of paper. If we do that, right, this turns into 0.1. And so then our KSP equals 0.1 plus x times 2x quantity squared. Because x is going to be very small, mathematically we can ignore it. And so we get 1.3 times 10 to the negative 6th equals 0.1 times 4x squared. And so now we can solve for x. So divide by 0.1, divide by 4, square root, we get 0.0018. Now, this is actually a good discussion, just to have the discussion. How does this concentration compare to that concentration, and why? So this is our common ion effect, right? It's the idea that if we already have some calcium here, it's going to shift the equilibrium back to the left a little bit, which means we're going to have less dissolving. And so in pure water, our concentration would be 0.0074. But in this calcium nitrate solution, because we already have calcium ions, less is going to dissolve, and it's going to be 0.0018. Okay, let's look at part C. So we're drawing, right? They always have, or at least they always have had, one drawing question on the free response, right? So you have to draw something, whether you're drawing a Lewis structure or you're drawing soluble ions. In this case, we're going there. So what they want you to do here is they say, in the box below, complete a particle representation diagram that includes 4, so make sure you draw 4 and don't draw any more, 4 water molecules with proper orientation around the calcium ion. Represent the water molecules as Mickey Mice, right? Yeah, Isabel can do the drawing for sure. Isabel's a good artist. All right, so what they want you to do is they want you to represent the waters like this. And what that is symbolizing is that's symbolizing, you know, we can think of it as like a Lewis structure, our water with its bent shape. Now, what do we know about water in terms of its polarity? O is partially negative. So the oxygen is pulling on the electrons because it has a greater electronegativity. And so it's going to pull on the electrons towards this direction. And so our oxygen end is going to be partially negative. and our hydrogen end is going to be partially positive. And so because the calcium ion has a positive charge, I'm sure they did. So then we want to surround our calcium with our waters oriented so that the oxygen faces inward, so that we can have an attraction between the negative end of the water and the positive dissolved calcium ion. Okay, let's check the grading key as the last thing, see how we did. So grading key, okay, we got to do the solubility, check. They didn't include the phases. Psh, lazies. So 1 point for the correct equation. We did the KSP calculation. We assume x is very small. We get the correct setup, which we did, ice table, etc. We get 1 point for this final answer. Got that, check. And then our drawing, ooh, they've got, look at them being all cutesy with their drawing. I think my diagram's a little more straightforward. Unfortunately, no, Micah. No extra points for that. The diagram should show the oxygen end on the water molecules closer to the calcium ions. Done. So easy. This problem you should have been able to get most of the points. You might have gotten lost on the math here, but this is definitely an easy 4 out of 4. So. Sorry, Micah. All right. Any last concerns? Like I said, I'll be in the Discord this afternoon to answer any questions. I'm going to upload the stream to YouTube so Mikey can go watch it, as well as any other who isn't currently viewing. Lauren, if you only got 0, it's okay. No, Bryce, technically. So those small nuances are discussed among the graders. So there's a group of people that will grade the exam, and they all come to a same consensus. Like, I'm sure on this problem, someone asked, oh, what if they write the phases and they write them wrong? The grading key doesn't have the phases. I'm sure they came to a conclusion on whether they took it or not. But since I wasn't a part of that conversation, I don't actually know. So... cool. So yeah, I'll upload I'll upload the grading key to tell you like how many points gave you what score, and then I'll also upload the 2016 exam so you have that, and you can work on it over the break. No streams next week because of spring break. No homework or anything. The next thing that's due is the 2016 exam in 2 weeks. Yep, cool. Have a wonderful spring break. I'll catch you guys in a week and a half. And if you have any questions or anything, make sure to send me an email or ask me in Discord this afternoon. Got it. I am streaming the esports games. So the high school team is competing. They have a scrim set up on Monday and Tuesday. So Micah, you can tune into those if you want to get some more channel points. I'll probably stream some other nights too. BYU has their class on Tuesday, Thursday, so I'll be streaming those nights. So anyways, we will catch you guys later.